You think you understand gravity. It's the most familiar force in the universe. You've been living with it since the moment you were born. Drop something, it falls. Jump up, you come back down. The Earth holds the moon, the sun holds the planets. Simple, obvious, natural. But that's not understanding, that's just familiarity. You've seen gravity a million times, but seeing something is not the same as knowing why it happens. And here's what nobody tells you. We don't know why gravity happens. Not really. We can describe it, we can measure it, we can predict it with absurd accuracy. But when you ask the deep question, when you ask why masses attract each other across empty space, physics has no answer. This isn't a temporary gap. This isn't something we're about to figure out next year. This is a fundamental limit on what explanation means. And understanding that limit, really understanding it, changes everything about how you see the universe. Let's start with what you think you know. Things fall. You drop a ball, it falls down. 16 feet in the first second. That's what Galileo measured. That's what you can measure right now if you have a stopwatch in a tall building. Drop something, count 1 second, it's fallen 16 feet. Simple experiment, reproducible result. Science at its most basic. But now think about the moon. The moon is up there 240,000 miles away going around the Earth. It's not falling down. It's staying up there orbiting, going in a circle month after month. That seems completely different from a ball falling, doesn't it? One thing falls straight down, another thing goes around in a circle. Two totally different phenomena, but they're not different. That's the genius. That's what Newton figured out. The moon is falling. It's falling toward the Earth right now as you read this, but it's also moving sideways, tangent to its orbit. And because it's moving sideways while it falls, it keeps missing the Earth. Falls toward us, but its sideways motion carries it past us. So it falls and falls and falls and never hits the ground. That's what an orbit is. Continuous falling while moving sideways fast enough to keep missing. The moon is a projectile. It's been falling for billions of years and it never lands because the Earth curves away beneath it as fast as it falls. Now here's where Newton did something extraordinary. He asked a simple question. If the moon is falling toward Earth, how fast is it falling? And can that be connected to how fast things fall here on the surface? The moon is 60 times farther from the center of the Earth than we are. We're standing 4,000 miles from the center. The moon is 240,000 miles away, 60 times the distance. Newton guessed that gravity might get weaker with distance. Specifically, he guessed it follows an inverse square law. If you go twice as far away, gravity becomes 4 times weaker. 3 times as far, 9 times weaker. The square of the distance. If that's true, then at the moon's distance, gravity should be 60 squared times weaker than here on the surface. That's 3,600 times weaker. On Earth, things fall 16 feet in 1 second. If gravity at the moon is 3,600 times weaker, the moon should fall toward Earth by 16 feet divided by 3,600 per second squared. Work out the geometry. Figure out how much the moon deviates from a straight line in 1 second as it curves around its orbit, and you get exactly that number. The moon is falling at precisely the rate Newton's law predicts. Two completely independent facts, how fast things fall on Earth and the orbital period and distance of the moon connected by one simple law. There's no going back after that. The law is real. Newton went further. He calculated what shape an orbit should have if gravity follows an inverse square law, and he found it should be an ellipse. And the planets do move in ellipses. Kepler had measured that already, but Kepler didn't know why. Newton explained it. Same law, same mathematics predicts the shape of planetary orbits. Then the tides. Why the 2 high tides per day? The moon pulls on the Earth. You'd think there'd be one bulge of water on the side facing the moon, but there are 2 bulges, 2 high tides every 24 hours. Why? Because the moon pulls on different parts of the Earth with different strengths. The water on the near side is closer to the moon, so it gets pulled more than the solid Earth underneath it. The water bulges toward the moon, but the water on the far side is farther from the moon than the solid Earth, so it gets pulled less. The Earth gets pulled away from that water, leaving a bulge behind. 2 bulges, 2 tides. Same law, same mathematics. Explains the shape of planets, why they're round, why they bulge at the equator when they spin, why the sun and stars are spherical. One equation, F equals G times M1 times M2 over R squared. Force equals a gravitational constant times the product of the masses divided by the square of the distance between them. It's almost miraculous how much falls out of that one simple formula. But now stop. I need you to notice something. Everything I just said is a description. I told you how gravity behaves. I told you the pattern, the mathematical law, the predictions you can make. I never told you why. Why do masses attract? What is it about having mass that makes you pull on other masses? What is reaching across that 240,000 miles of empty space between the Earth and the Moon to make them affect each other? Nothing. There's nothing there. That's the problem. Newton himself was deeply bothered by this. He wrote about it. The idea that one body could act on another at a distance through a vacuum, with nothing in between, with no contact, no mechanism, no explanation. He called it an absurdity. He said no one competent to think philosophically could believe such a thing. And yet, that's exactly what his law describes. Gravity acts at a distance, instantly. The Earth pulls on the Moon, and there's nothing but empty space in between. No rope, no pressure, no medium transmitting the force, just action at a distance. You're comfortable with this because you've heard it your whole life. But stop and think about what you're accepting. You're accepting that objects can influence each other across vast stretches of emptiness with no contact, no mechanism, no explanation. That's not obvious. That's bizarre. In your everyday experience, forces require contact. You push a chair, you touch it. You throw a ball, your hand touches it. Forces come from things bumping into other things. But gravity doesn't work like that. Gravity reaches across space and grabs you with nothing in between. Now, you might say, well, we figured that out. Einstein explained it. Gravity isn't action at a distance. Gravity is curved space-time. Masses bend the fabric of space, and other masses follow that curvature. The Earth isn't pulling on the Moon. The Earth is curving the space around it, and the Moon is just moving in a straight line through curved space. Fine, that's a beautiful picture. And it makes predictions that Newton's gravity doesn't, predictions about how light bends near massive objects, how time slows down in gravitational fields, how black holes form. General relativity is extraordinarily accurate, but you haven't explained anything. You've redescribed it. Instead of saying masses attract, you're saying masses curve space and objects follow the curvature. That's a different description. It's mathematically more powerful. But it doesn't answer the question, why does mass curve space? What is it about having mass that bends the geometry of the universe? Einstein's equations tell you how much curvature you get for a given distribution of mass and energy. They don't tell you why mass curves space in the first place. This is the thing nobody wants to hear. There is no why, not at the fundamental level. Physics gives you descriptions, patterns, mathematical laws that let you predict what will happen. It doesn't tell you why those laws hold instead of other laws. It doesn't explain why the universe has these rules rather than different rules. You can ask why ice floats on water. I can tell you it's because ice is less dense than liquid water. Why is it less dense? Because the molecular structure has more space between molecules. Why does it have that structure? Because of how hydrogen bonds arrange at freezing temperatures. Why do hydrogen bonds arrange that way? Because of quantum mechanics, the Schrödinger equation, the Pauli exclusion principle. At each step, I'm giving you a deeper answer, but I'm also just pushing the question back one level. Eventually, you hit bedrock. You hit the fundamental equations, the basic forces, and there, the only honest answer is, that's what we measure. That's how the universe behaves. The chain of why has to end somewhere. Gravity is one of those endpoints. We can describe it, we can calculate it, we can test it, but we can't explain it in terms of something more fundamental. Not yet, maybe not ever. Here's another thing that should bother you. Gravity is weak, absurdly weak, the weakest of the four fundamental forces by a laughable margin. Take two electrons, put them a centimeter apart. They repel each other electromagnetically because they both have negative charge. They also attract each other gravitationally because they both have mass. Compare those two forces. The electromagnetic repulsion is 10 to the 42nd power times stronger than the gravitational attraction. That's a 1 followed by 42 zeros. The electromagnetic force is so overwhelmingly stronger than gravity that gravity might as well not exist for electrons, for atoms, for molecules, for anything at the scale of ordinary matter. So why does gravity dominate the universe? Why is it the force that shapes galaxies, holds planets in orbit, pulls you to the ground? Because gravity only attracts. It never repels. And because it affects everything with mass. Electromagnetic forces are strong, but they come in positive and negative. Most matter is neutral. The positive and negative charges balance out. The enormous attractive and repulsive forces cancel, leaving a net effect near zero. But gravity has no negative. There's no anti-mass, no gravitational repulsion. Every bit of mass in the universe attracts every other bit. And while each individual attraction is pathetically weak, there's no cancellation. It all adds up. When you have a planet's worth of mass, trillions of tons all pulling together, that weakness becomes irrelevant. The tiny forces add and add and add, and you get something strong enough to hold atmospheres, crush matter into stars, curve light around galaxies. Gravity wins by accumulation. It's the tortoise, not the hare. Weaken every individual interaction, dominant at cosmic scales because it never gives up, never cancels, never switches off. Now here's something that should keep you awake at night. There's a coincidence in gravity that has no explanation. It's so strange, so arbitrary, so inexplicable that Einstein built his entire theory of general relativity around it. And we still don't know why it's true. There are two completely different ways to think about mass. First, there's inertial mass. This is how much an object resists acceleration. Push on something and see how hard it is to speed up or slow down. That resistance is inertial mass. Heavy objects are hard to accelerate. Light objects are easy. Second, there's gravitational mass. This is how strongly an object interacts with gravity, how much it pulls on other objects, how much other objects pull on it. This determines the strength of gravitational attraction. These are conceptually different things. One is about resistance to motion. The other is about strength of a force. There's no logical reason they should be related. They're measuring different properties, but they're equal, exactly equal. Every experiment ever done confirms this. The inertial mass of an object is precisely equal to its gravitational mass. Galileo's experiment dropping different masses and seeing they fall at the same rate, that's a consequence of this equality. If inertial mass didn't equal gravitational mass, heavy objects would fall at different rates than light objects. Why are they equal? Nobody knows. In Newtonian physics, it's just a coincidence. You write down the equations, and it happens to work out that these two masses are the same. But there's no reason, no explanation, just a brute fact. Einstein looked at this coincidence and built a theory around it. He said, maybe they're equal because they're the same thing. Maybe gravity isn't a force at all. Maybe what we call gravitational acceleration is actually inertial motion through curved space-time. An object in free fall isn't being pulled by a force. It's moving in a straight line through curved space. And the equivalence of inertial and gravitational mass follows automatically because there's only one mass to begin with. That's elegant. That's beautiful. And it makes general relativity work. But it still doesn't explain why mass curves space. It just relocates the mystery. Let me make this concrete. You're sitting in a room. You feel your weight pressing you into the chair. You feel the floor pushing up against your feet. That's gravity pulling you down, right? Now imagine you're in a rocket ship, far from any planet, accelerating upward at 8 meters per second squared. You'd feel the exact same thing, the floor pushing up against you, your weight pressing into the seat. You could not tell the difference. No experiment you could do inside that room would distinguish between being in a gravitational field and accelerating through empty space. That's the equivalence principle. Gravity and acceleration are indistinguishable. This is what led Einstein to general relativity. If you can't tell them apart, maybe they're the same phenomenon viewed from different perspectives. But this just pushes the mystery deeper. Now, instead of asking why masses attract, you're asking why space-time curves and why objects move along geodesics through that curvature. The question has changed form. It hasn't been answered. Here's what you need to understand about how physics actually works. We don't start with philosophy and derive the universe. We start with observations. We see patterns. We write equations that describe those patterns. We test those equations against new experiments. When the equations work, when they let us predict things we haven't seen yet, we say we understand the phenomenon. But understanding in physics doesn't mean philosophical satisfaction. It doesn't mean matching your intuition. It means predictive power. It means being able to calculate, to predict, to build technology that works. By that standard, we understand gravity extraordinarily well. We can send spacecraft to Pluto, slingshot them around Jupiter, land them on comets. We can predict eclipses centuries in advance. We can detect gravitational waves from colliding black holes billions of light years away. The theory works, but the theory describes. It doesn't explain why. And at the fundamental level, we have to accept that. The universe doesn't owe you an explanation that makes you comfortable. It doesn't owe you a story that matches your intuition about how things should work. Your intuition evolved to throw rocks, pick fruit, avoid predators. It did not evolve to understand why masses attract each other at a distance or why space itself can bend. When physics reveals something that violates your expectations, you have two choices. You can reject it as unsatisfying and keep demanding better explanations that don't exist. Or you can expand your intuition, learn the mathematics, work through the problems, build new mental models based on equations and experiments, not everyday experience. The beautiful thing about gravity is this. It's the force you've known the longest, the force that seems most obvious. And it turns out to be the strangest one of all. It's the weakest force in nature, yet it shapes the universe. It acts at a distance with no mechanism. It makes time and space bend. It has a mysterious equivalence built into its structure that nobody can explain. Every other force you can at least imagine reducing to something simpler. Electromagnetic forces are mediated by photons, the strong nuclear force by gluons, the weak force by W and Z bosons. There's a picture, a mechanism, particles carrying the force from one place to another. Gravity doesn't fit that pattern. We've been trying for decades to find gravitons, the hypothetical particles that would carry gravitational force. We haven't succeeded. And there are deep theoretical problems with quantizing gravity, with making it fit into the same framework as the other forces. Gravity remains apart, unique, fundamental in a different way than the others, the force that refuses to be explained. And yet we use it every day. Your GPS works because we understand gravity and relativity well enough to correct for time dilation in the satellites. We land robots on Mars by calculating trajectories through gravitational fields with extreme precision. We've detected ripples in space-time from events that happened billions of years ago. We don't understand why gravity works, but we understand how it works well enough to do extraordinary things with it. And that's what physics offers. Not comfort, not satisfying stories, not explanations that make the universe feel familiar. Physics offers power, control, the ability to predict and manipulate nature. The next time you feel your weight pressing you into your chair, remember what you're actually experiencing. You're experiencing a fundamental force of nature, one of four in the entire universe. A force that acts across empty space with no mechanism. A force that bends the geometry of the cosmos, a force that connects you to every piece of matter in the universe, however faintly. You're feeling something that nobody on Earth can fully explain. Not me, not Einstein, not Newton. We can describe it with extraordinary precision. We can use it to send machines to other planets. We can detect it rippling through space from the other side of the observable universe. But we don't know why it exists. We don't know why masses attract. We don't know why space bends. We don't know why inertial and gravitational mass are equal. Some people find that frustrating, but I find it beautiful. It means there's still mystery at the foundation of everything. It means the universe is deeper than our current understanding. It means that every time you drop something and watch it fall, you're witnessing something fundamental, something unexplained, something that connects you to the largest structures in the cosmos. You've been living with gravity your whole life. You thought you understood because it was familiar. But familiarity is not understanding. And the truth is far stranger than the familiar story. Objects don't fall because the Earth pulls them down. Objects fall because they're moving through curved space-time, following paths that mass has bent into existence. And why does mass bend space-time? Why do objects follow those paths? Nobody knows. That's where the chain of explanation stops. That's bedrock. That's the universe showing you its structure without telling you its reasons. And that's what makes gravity the most mysterious force of all. Not because it's complicated, not because the mathematics is hard, but because it's fundamental. Because there's nothing underneath it. Because when you ask the deepest why, The universe just stares back at you and says, this is how it is. That's not a failure. That's the frontier. That's where we are right now. We've figured out how the universe behaves. We're still figuring out what that tells us about reality itself. And in the meantime, things keep falling. The moon keeps orbiting. Galaxies keep spinning. And gravity keeps working, whether we understand it or not.